Hi everyone, this is another self-quiz. Today, this topic is over calorimetry. So this is a solution calorimetry problem that's pretty common. It's one I believe you guys did in lab. So maybe not this exact one, but similar to. So the setup is that sodium bicarbonate, which we also call baking soda, will react with acetic acid, aka vinegar, according to the reaction that I gave you here. This is the full reaction, and it's already balanced. All right. If 8.40 grams of sodium bicarbonate is added to 100 milliliters of 1.0 molar acetic acid, the temperature of the solution is found to decrease from 22 to 16.5 degrees Celsius. Calculate A, the Q for the water, heat for the water, B, the heat for the reaction, and C, the delta H for the reaction. Go ahead and pause the video at this point. Take a few minutes to try to solve it. Make sure you have, your calculator and your periodic table and everything ready to go. And once you're done, hit play and I'll go through the answer. Okay. All right. So with these where you have a lot of information going on, I like to reorganize the data under the reaction equation. So I've got that I have 8.4 grams of sodium bicarb. So I'm going to put that here, 8.40 grams. We also know that we have 100 milliliters of 1 molar acetic acid. So we have 100 milliliters, 1.0 molar acetic acid. And then we have this temperature information as well. I don't have anywhere particular to put it, but we'll highlight it just to be ready to go. All right, so the first thing we have to do is calculate the Q for the water. So remember that whenever you're calculating Q, we're going to use the equation Q equals Cm delta T. C is the heat capacity, M is the mass, delta T is the change in temperature. One thing that's important to remember here is that delta T is always the T final minus the T initial. So that's going to become important here in just a minute. We always do this for solution reactions as though the solution is entirely water. So we're going to pretend that this 100 milliliters of water of solution we have. So we have 100 milliliters of the 1 molar acetic acid. We're going to pretend that that's 99% water, which is close enough to 100% water. And we're going to run with that as our water. So the Q for the water then is going to be 4.18 joules per gram degree Celsius. Please include your units. And that is not a C. It doesn't look like one. Degrees Celsius, close parenthesis. Now the mass here is going to be the mass of our water. We're going to make an assumption here, which is not the greatest assumption in the world, but it's close enough. We're going to assume that if we have 100 milliliters of solutions, that's close enough to 100 grams of water. And then our T final, the temperature, notice the temperature goes from 22 to 16.5. So T final is 16.5 degrees Celsius minus 22.0 degrees Celsius. That was our initial temperature. And your Q for your water now, when we plug that through, 4.18 times 100 times 16.5 minus 22.0. That's going to come out to be negative, and that's not a mistake, negative. Let's see, we need to have, when you do this, I should have shown this out. 16.5 minus 22.0 is negative 5.5. So that's got two significant digits. So this is going to be negative 2300. Notice your grams and your Celsius cancel. So that's going to be joules. All right. So the fact that we had a negative delta T over here explains why we have a negative Q. All right. So now, remember that this is to find the Q for the reaction. We're just going to use the simple relationship that the Q of the system and the Q of the water are negative of each other. In other words, Q1 equals negative Q2. All right, so we're just going to change the sign and say that the Q for the reaction is the opposite of the sign for the Q for the water. So that's going to be positive 2,300 joules. All right. Folks get confused a lot of times at this point because they want another equation to calculate the Q for the reaction, and it's simply a matter of remembering that whatever the Q for the reaction is the opposite of the Q for the water. All right. So now we've got to calculate the delta H. This is a little trickier. The delta H, remember, is the Q for the system divided by the number of moles of the limiting reactant divided by its coefficient in the reaction equation, which is a little annoying because we got to figure out which one's limiting reactant here. So we'll do kind of a side calculation here. We have 8.40 grams of sodium bicarbonate. The molar mass of sodium bicarbonate is 84.01 grams per 1 mole of sodium bicarbonate. All right, so that's going to come out to be 0.100 moles sodium bicarbonate. And then for the acetic acid, we have to use the molarity equation to get the number of moles. So that's going to be moles over liters. We know the molarity is 1.0. We don't know the number of moles, but we know the liters is 100 milliliters, which is the same as 0.100 liters. So we cross multiply here. Remember, this is an understood one. So X comes out to be 0.100 moles of HCl, or excuse me, acetic acid. So that means that we have the same number of moles of sodium bicarbonate as we do moles of acetic acid. So neither one of them is limiting, or they're both limiting, however you want to think about it. So and remember that back up here in the reaction equation, they both have a coefficient of 1 here. So in both cases, it's 0.1 divided by 1, which is 0.1. So that's our N value. So now to find delta H, now it becomes pretty easy. So we've got delta H equals positive 2,300 joules divided by 0.100 moles. Delta H, technically this is delta H naught. I haven't emphasized this a whole lot yet. This becomes more important later on, but for now, don't worry too much about it. So that becomes 23,000 joules per mole. And we could also express that as positive 23 kilojoules per mole. That would be fine too. Notice that that the fact that delta H is positive, that means this reaction is endothermic. And we remember from earlier in the semester that endothermic reactions absorb heat into them, and therefore they cool the surroundings, which fits with our observation over here that we had a negative delta T. Okay, so those things all sync up, and is one way to double check yourself at the end. All right, so when you're doing these calorimetry problems, they look more complicated than they are. Remember that to calculate the Q for the water, you're going to use Q equals Cm delta T. The mass is usually going to come from the mass of the solution. If you're not given a mass, we're going to assume a density of 1 gram per mil for the water and use the volume to convert to grams. All right. Then to get the Q for that's the Q for the water. To go to the Q of the reaction, we have to flip the sign. All right, because they're always opposite. And then to get delta H, we have to find Q over N, which requires us to find the N value, which requires a little bit of stoichiometry, maybe remember the molarity equation, and then plug that in Q of the system over moles. And as a last step, just double check that the sign of your delta H makes sense based on your delta T.